Hello everyone, welcome to my channel. In this lecture, we will discuss about the adsorption of 2,4-dichlorophenol with the help of Aspen adsorption. We will use activated carbon to adsorb 2,4-dichlorophenol from paper and pulp industry. As we know that the effluent of paper and pulp industry consists of various components, various pollutant, and 2,4-dichlorophenol is one of the toxic component which coming out from the paper and pulp industry. So in this lecture, we will use the activated carbon to adsorb this component from the paper and pulp industry. We will use the activated carbon. We can use other adsorbent like the bagasse fly ash. We can also use rice husk fly ash to adsorb the 2,4-dichlorophenol. But in this lecture, we will only use the activated carbon to adsorb 2,4-dichlorophenol from the paper and pulp industry. So this is a paper related to the adsorption of 2,4-dichlorophenol, and this is the introduction. Here you can see that the paper and pulp industry effluent usually consist of various chlorinated organic compound, and these compounds are hazardous and toxic. So their concentration in the paper and pulp industry effluent should be small, or we should decrease the concentration of such component in order to reduce various diseases in human being, plant as well as in animals. In this lecture, we will use the activated carbon, and these are the material we will use the Aspen adsorption. This is the feed. This is the feed requirement. We will use the fake bed column to remove the 2,4-dichlorophenol. There will be the feed will enter to the fake bed column. The fake bed column will consist of activated carbon, and such activated carbon particle will remove the 2,4-dichlorophenol from industrial wastewater, which usually consists of 2,4-dichlorophenol. And in the product flow rate, there will be no, or there will be very less concentration of 2,4-dichlorophenol. So the feed requirement is here you can see we can use various initial concentration of the component in the feed flow rate. But here I'm assuming, here you can see in this paper, they have used the phenolic initial concentration in the feed is this one 1.22 multiplied by 10 raised to 4 minus 4 kilomole per cubic meter. So you can use various concentration of dichlorophenol in the feed stream. So here I will use this one 1.22 multiplied by 10 raised to 4 minus 4 kilomole per cubic meter. This is the concentration of dichlorophenol in the feed stream, and the volumetric flow rate of the feed stream is 2 cubic meter per hour. You can use other concentration, other volumetric flow rate in order to see the effect of the volumetric flow rate on breakthrough curves. Our main focus in this lecture will be to plot the breakthrough curve for the dichlorophenolic compound. We will plot the breakthrough curve for such component, and breakthrough curve is nothing but it shows the concentration of component in the product stream. So when the concentration of dichlorophenol in the product stream reaches to 95% of the feed stream concentration, then we will obtain the breakthrough time. So from this breakthrough curves, we can obtain the breakthrough time, and after this, after breakthrough time, we can stop our feed flow rate. We After stopping feed flow rate, we can regenerate our activated carbon or our catalyst or adsorbent in order to enhance the adsorption process. So our main focus here is to plot the breakthrough curve, and once breakthrough curve is obtained, we will stop our flow rate we will regenerate the adsorbent, and again we will start the experiment. This is the feed volumetric chloride. This is the component concentration in the feed stream, and the product stream. In the product stream, we will select zero. There will be no in the product stream. There will be no dichlorophenolic compound. And the feed temperature, we will select the feed temperature to be 30 degrees centigrade, and the feed pressure will be 3 atmospheric pressure. Okay, this we will use this is as you know, this is the fag bed column. There will be here you can there will be activated carbon particle in this fag bed column. This is the feed stream, consists of the 2,4-dichlorophenol, which are coming out from the paper and pulp industry. So once the feed is entering to this fag bed column, the 2,4-dichlorophenol will attach to the surface of the adsorbent particle, which is activated carbon in this case. And once the 2,4-dichlorophenolic compound is adsorbed, the product stream will coming out from the fag bed column. So we will check the concentration of 2,4-dichlorophenolic compound in this product stream. Once the concentration of 2,4-dichlorophenolic compound in this product stream reaches to 95% of this concentration, we will stop the flow rate. We will regenerate this column, and we will start again this process. So we will continue the process again. We can regenerate this activated carbon by washing or um, uh, by already dissolving agent. We can regenerate this column. Okay. So first of all, we will go to and this. Remember, in this paper, the author used three adsorbent activated carbon, rice husk, and bagasse adsorbent. But here I'm using the activated carbon only. So this, as you know, this is the property of the adsorbent. This is the bagasse fly ash property, bulk density, average particle void ratio, etc. Surface area. This is the rice husk fly ash property. This one, these, and the activated carbon property or bulk density is 617.5 kilogram per cubic meter. Average particle size of the activated carbon is 0.002 meter, and the for volume is this one, and the specific surface area of the activated carbon is 847 square meter per gram. We will use the isotherm in this Aspen Adsorption. We will use isotherm, and the isotherm we will use the isotherm we will use the phenolic isotherm in this case, because we can use another isotherms depend on your experiment. So if you perform experiment in lab and you know that your lab experiment follow the Langmuir, so you can use the Langmuir isotherms. But here we will use the phenolic isotherm, and the phenolic isotherm here you can see this is the phenolic isotherm. This is the equilibrium uptake obtained with the help of phenolic isotherm. This is the phenolic constant Kf, and 1 over n. The n 1 over n show the affinity between adsorbent and adsorbate. The adsorbate in this case is the 2,4-dichlorophenol, which are present in the wastewater, which are coming out from the paper and pulp industry, and the adsorbent is the activated carbon. So the adsorbate will attach on the surface of the adsorbent, which is activated carbon in this case, and we will remove the adsorbent with the help of adsorbent. With the help of adsorbent. So these are the constant. K is the constant, 1 over n, or n is the constant. So here you can see the n. This is the activated carbon. These are the other adsorbent, but we will focus on this activated carbon. The phenolic isotherm constant, here you can see the milligram per gram, and this is the unit of this one. So this is the phenolic constant value for activated carbon, and this is the n, the affinity factor between which show the affinity, the factor which show the affinity between adsorbent and adsorbate. It is 2.74 to 5. This one, the n has no value, no unit, and this is the unit of Kf, the Freundlich constant. You can obtain this unit by conversion or by rearranging the Freundlich equation. So this is the equilibrium of take. So This equilibrium of take can be experimentally, you can obtain this equilibrium of take with the help of various experiments, lab experiments. And this equilibrium concentration can also be obtained with the help of the lab experiments. So you can obtain this equilibrium of take from initial concentration in the lab. So you can UV visible spectrophotometer. From the spectrophotometer you can also obtain. You can also obtain the concentration by using by other methods also. But here we will use the activated carbon, and this is the mass transfer coefficient. And this is the unit of mass transfer coefficient, and 1 divided by minute. And for activated carbon, mass transfer coefficient value is this one. Okay. This is the initial concentration of the fluid. Here you can see the initial concentration of the fluid is this one, volumetric flow rate, temperature, pressure, etc. So now we will go to the Aspen adsorption. Go to the Aspen adsorption, open Aspen adsorption. And from the Aspen adsorption, in the Aspen adsorption, we will plot the breakthrough curve. Close this one, go to the component, click on configure property, click on use Aspen property system, click on edit using Aspen property. So here we will add our component. Our component is the 2,4-dichlorophenolic compound. We will add this component from Aspen plus to Aspen adsorption. So now I'm adding my component from the Aspen plus to Aspen adsorption, because in Aspen adsorption there is no component. We cannot add a component in this Aspen adsorption library. So we will add the component from the Aspen plus library. So now you can see this one plus is open. So we will go to the component. In this one plus, we will add the component. Either if you have formula of the 2,4-dichlorophenolic compound, you can directly add the component. But 2,4-dichlorophenol is some complex compound, and we can add the component from this one. Click on find. So it is 2,4-dichlorophenolic compound. Dichloro R2,4-fluorophenolic phenol 2,4-dichlorophenol. Its molecular weight is about 163 gram per mole. So if you can check it from the online sources. So here there's no match. I will add dichlorophenol. So it will take some time. Dichlorophenol. Now we will maximize this one. Here you can see the compound name, the data bank, and here you can see 2,4-dichlorophenol. Its molecular weight is this one, about 163 gram per mole. This one 2,4-di, 2,5-dichloro, 2,6, but this one 2,4-dichlorophenol, and this one 2,4-dichloro. Click on select compounds. Click on close. Okay, so it is added. We added the component in the Aspen plus. Now we will click on next. So as we know that the 2,4-dichlorophenolic compound is an organic compound. It is a phenolic compound, chlorinated phenolic compound. It is halide, the halide of phenol. Usually most of the organic compound follow the equation of the Finn-Robinson equation of state. So we usually use the Finn-Robinson equation of state for organic compound, and this one is the organic compound. So we will use the Finn-Robinson equation of state for this one. You can use another equation which is suitable for organic compound, but I'm using the Finn-Robinson equation of state. For this organic compound, click on next and click on OK. And now go to the Aspen adsorption, click on OK. Again go to this one plus and click on yes. So go to the Aspen Adsorption again. So now it will take some time. So we added our component from Aspen plus to Aspen Adsorption. Go to the default. Here you can see this is the water H2O. Click on this one and here you can see available compound. I have added this component from Aspen plus to Aspen Adsorption. Now I want to add this component from Aspen plus to Aspen Adsorption library. So this is Aspen the component and I'm adding. So I have added and okay I added this one. So I have added the component dichlorophenol from Aspen plus to Aspen Adsorption. Now I will float. I will make the flow sheet. So this is a liquid process. This is the liquid because the textile industry, the liquid, the wastewater which are coming out from the textile industry are liquid, and the phenolic compound is present in the wastewater. So this is the feed, liquid feed, the liquid bed. Here you can see is the liquid bed. This is the icon. You can change the icon from this one to this one. Okay, this is the bed, gas bed. This is the liquid bed. Here you can see you can the gas dynamic, liquid ion exchange, etc. These are various. You can design the ion exchanger, the gas bed, the bed designing a peg bed for gaseous component. So I'm using the liquid bed. This is the liquid feed. Here you can see liquid feed, liquid product, and the liquid bed. So liquid bed, liquid product, and liquid stream. This is the connection. So liquid stream, here you can see gas connection. This is for gaseous problem, and this is for the ion exchange from liquid connection. Now add the feed to the bed, add bed to the add product to the bed, and now this is the feed. Double click on the feed. You can rename. For example, you can rename. Click on this one, and here rename block. So you can rename it like this one feed. Click on OK. Now this is feed. Here you can see feed. This is bed. So you can rename the block. So this is suppose this is the adsorption column. ADSO or B adsorber or adsorption column. So this is my adsorber. Click on OK. Okay, you can drag this one. Okay, this is the product. Rename. For example, rename. This is the product. This is the product. Okay. So this is the feed, which consists of the 2,4-dichlorophenolic compound, and these feed is coming out. These are coming from the paper and pulp industry. It is entering to the fake bed column, and in the fake bed column there is activated carbon, and the activated carbon adsorb the 2,4-dichlorophenolic compound from the wastewater, and this is the outlet. This is the product, and in the product stream we have very little concentration of 2,4-dichlorophenolic compound. Okay, this is the diagram. Now click on the field. Specify the field. Is the reversible process? Okay. Speed. So the volumetric flow rate of the field is here you can see the field is specified. The volumetric flow rate of the field is 2 cubic meter per hour. You can use another for your experimental work. You can use 3, 4 like this one. Yeah, the other use various flow rate in order to plot the breakthrough curve. Usually if we changes the change is this volumetric flow rate to see the effect of volumetric flow rate on breakthrough curve. They also change this concentration and check the effect of this concentration on the breakthrough time and breakthrough curve. You can also change the temperature and go from isothermal to non-isothermal process. But here I'm using the volumetric flow rate 2 cubic meter per hour or 2 cubic meter per hour. This is the volumetric flow rate of my feed stream, which are coming out from the textile industry and which are entering which are coming out from textile industry and going to the and entering to the adsorption column 2 cubic meter per hour. not second but 2 cubic meter per hour. Here you can see for cubic meter per hour, so 2 cubic meter per hour. Okay. Now this is the concentration. The concentration of 2,4-dichlorophenolic compound in the feed. So the concentration is in the this is a unit. It can be molarity or kilomole per cubic meter. Here you can see mole per liter molarity. This is the so if you have lab experiment and you have molarity of your component. Suppose you have some other, like you have lead concentration. Suppose you have prepared a 2 molar lead solution. So you can directly add like this one, 2 mole per liter and 2 for your lead component. So this is just various units. So the feed, here you can see the feed 1.22 kilomole per cubic meter. 1.22 kilomole per cubic meter. 1.22 multiplied by 10 raised to the power minus 4. So for multiply by 10 raised to the power, you can use E and minus 3. So 1.22 multiplied by 10 raised to the power minus 4. Here you can see 1.22 multiplied by 10 raised to the power minus 4 kilomole per cubic meter. Kilomole per cubic meter. Kilomole per cubic meter. Okay, 1.22 multiplied by 10 raised to the power minus 4. 1.22 multiplied by 10 raised to the power minus 4. Okay, you can see, and the feed temperature is in degree centigrade, 30 degree centigrade. You have already discussed this one, and this is the 3. The feed pressure is 3 bar, 3 atm. 3 atmospheric pressure is 3. So okay, here you can see that feed temperature is this one, pressure is this one. Okay, the product the concentration of the 2,4-dichlorophenol in the product stream is 0 for the breakthrough curve. So we will assume this one to be 0. So in the beginning, there will be no the concentration of the 2,4-dichlorophenolic compound in the product stream will be 0. This is free. This free. This can be this one or other value. So when we start this Aspen adsorption dynamic process, this will automatically change. This is free. Okay. Close this one. Now we will go to the bed. Double click on the adsorber, and here you can see number of layer within the bed. The number of adsorbent layer inside the fake bed column is 1. So there is one layer of the activated carbon. There is one layer of activated carbon material inside the fake bed column, and the height. So this is and what is the height of this activated carbon inside this column? So the height of the activated carbon in this layer or the height of the adsorber is given to us, and the diameter, there is no value given in the paper, so I will assume 0.1 meter. So 0.1 meter will be the diameter of this column, and this is the inlet flow rate, and this is the outlet from the fake bed column. This is activated carbon is present inside this column. Okay, click on this one, and here we will add some momentum and material energy assumption and some kinetic model, etc. Here you can see the general material and momentum balance, kinetic model, isotherm, energy balance, procedure, etc. So general, here you from the discretization method, select discretization method for this problem. So I'm using the UDS1, the upward difference method 1, and there will be 20 number of node. So the discretization method, the other use this discretization method UDS1, 20 number of mode. The convection, the material and convection, the material and momentum or material and momentum balance, they used the convection with estimated dispersion. Here you can see the material convection with estimated dispersion, and the pressure drop assumption is none, and the velocity is constant. None and velocity is constant. For the kinetic model, the film model assumption is solid. So the film model assumption is solid. You can use the fluid. Film model assumption is fluid. It shows that outside the adsorbent, if the mass transfer is controlled by the liquid film surrounded by the adsorbent particle, then we will use the liquid film model assumption. But in this case, we will use the solid and the kinetic model assumption, the linear lump resistance. Can be the quadratic resistance. So this shows the resistance, the resistance to the transport of material. So when the 2,4-dichlorophenolic compound is transported from the bulk concentration to the surface of the activated carbon, so it will pass through various resistances. Actually, this limb resistance was. Information about that resistances. So it will be linear resistance and the form of mass transfer coefficient is constant. And the constant mass transfer coefficient value is given to us, this one. You can obtain this mass transfer coefficient constant from various equations. Okay. And from the isothermal, we can use various isotherms. Like for the adsorption process, we are usually use isotherm like Langmuir isotherm, like this one is the Brand-like isotherm. This is the equilibrium uptake. This is the equilibrium concentration, and this is the N, which was the affinity between adsorbent and adsorbent. Okay. So we will use the Brand-like one isotherm, and the one is for the constant temperature. Okay. Frantic one isotherm, energy balance isothermal process. So when the 2,4-dichlorophenolic compound is added to the surface of the activated carbon, so in that case there will be no heat released, there will be no heat absorbed in that case. So we assume that the process is isothermal, but in reality the process cannot be isothermal. In the absorption process, the heat can be released, and in most cases, heat are releasing in the absorption process. In very limited cases, the absorption process can be endothermic. So this is isothermal. This is the isothermal process. Okay, there is no heat is releasing or absorbing during the process. We can use a non-isothermal non-conduction, non-isothermal fluid phase conduction. So heat is releasing and energy is transferring in the fluid phase, like in the liquid phase, the heat is moving from liquid to the surface of the adsorbent. So we will use this one. You can use this one or other like this. But here we will ignore other. Just focus on this one. This is the procedure. Okay. Now click on specify. Specify the bed height. So the bed height, what will be the height of my adsorber? The height of the adsorber layer. So I assume that the height of the adsorber is equal to the height of my adsorbent layer. So the height of my adsorbent layer is 2 meter. Suppose I am using 2 meter here. You can see 2 meter. You can use 1 meter, 2, 3, 4, and you can see the effect of the height of adsorbent on the breakthrough time. You can see the effect of the height on the breakthrough time, the adsorbent uptake, etc. So I assuming 2 meter, though my adsorbent height is 2 meter. What is the internal diameter of the adsorbent layer? So I'm assuming this one 0.1. You can use 0.3, 0.4 meter, 0.5 meter, and this is the interparticle void edge. Actually, this is the void fraction. This shows the void fraction of the bed. So the void fraction is nothing but it is the it shows the distance between the distance between two particle inside the fake bed column. So in the fake bed column, we usually place the activated carbon particles. And when we place activated carbon particle, then there should be some distance between particles inside the packed bed column, and such distance are denoted by the interparticle void edge. Another void edge is the intraparticle void edge, and the intraparticle void edge of the particle is nothing but it shows the porosity of the particle. But here there is no intraparticle void edge, simple interparticle void edge, and interparticle void edge for most packed bed column is 0.4. So for most fake bed column, the interparticle void edge is 0.3 or 0.4 or 0.4. It is usually from 0.3 to 0.45. So just I'm assuming this value. The adsorbent particle radius. So this is the radius of the activated carbon particle. We are using the spherical activated carbon particle, and the radius of the activated carbon particle is what is the radius? So here you can see it is It is given the radius. Here you can see the diameter, the average particle size. So this is the diameter of the activated carbon particle. So the diameter is this one, so the radius will be this divided by 2, because diameter divided by 2 is the radius. So it is 0.001, 0.001 meter. This is the radius of the adsorbent particle. The density, the solid density, the bulk density of the adsorbent is given to us. So this is the bulk density of the activated carbon, and you can obtain this from experiments. This density, this porosity, you can obtain these value from experiments. So the density of the bulk density, there is the particle density and bulk density relation. So the bulk density is equal to particle density multiplied by 1 minus porosity, which is 0.4 in this case. So the bulk density divided by 1 minus porosity will be equal to the particle density. So this value divided by 1 minus 0.4, and 0.4, this is the interparticle voidage, this one. So when we divide uh, this one 617.5 divided by 1 minus 0.4. 1 minus 0.4 is equal to 0.6. So 617 divided by 0.6, it will be equal to 1029.166. Here you can see, you can use your calculator to obtain this value. 1029.16. Because just use calculator to check the value. This one, like 617, 617.5, sorry, point 617.5 divided by 0.6, 0.6 is equal to 1029.166, 1029.166. And this is the constant mass transfer coefficient. This is obtained from equations, and it is given here, constant mass transfer coefficient. The constant mass transfer coefficient is this one, in 1 over minute unit. It can be in 1 divided by second, but here this is in 1 divided by minute. 0.018 per activated carbon. So 0.01863, 0.01863, 0.01863, like the mass transfer in 0 in minute. So I will change it to minute. 0.01863. Let's check it. 0.01863. Okay, the isothermal parameter IP1, the isothermal parameter of the Freundlich constant, because the isotherm here we are using the Freundlich isotherm. So the isothermal parameter 1 is the Freundlich constant, and isothermal parameter 2 is the N, which show the interaction, the affinity between adsorbent and adsorbate, and their value are given to us. So their value are given to us, like for activated carbon, the Freundlich constant are these one. For this, for other like rice husk activated, rice husk adsorbent, fly ash adsorbent, the value are these one. But for activated carbon, value are this one. So the Freundlich constant value is this one. We will copy this one, and this is the isothermal parameter number 1. Because this is the isothermal parameter number 1, okay, and isothermal parameter number 2. Isothermal parameter number 2 is this one. Isothermal parameter 2 is this one. Okay. Now close this one, close this one, close this one. Double click on adsorbent. This is the 20, etc. This is the number of node, and these are, we have specified these value, like isothermal solid, Freundlich isotherm, isothermal momentum, convection with this one, lump resistance constant, specify, we have specified, etc. Here you see the specific direction is 0. We are selecting this is 0.4. Okay. Now click on initialize, click on yes, click close this one, close this one. Now we will, first of all, we will initialize our column. Initialize, Click on this one. Run is completed. Now we will plot the adsorbent, the breakthrough curve for this component, and so the breakthrough curve. So we will go to this plot, click on this one, and breakthrough, simply drive breakthrough. This is breakthrough curve, and now click on the product, drag this one, the results. So here you can see there is no 2,4-dichlorophenol compound in this product stream in the beginning. So after a certain time, the concentration of the 2,4-dichlorophenolic compound will be increasing, because with the passage of time, the activated carbon will saturated, and the component will be coming out in the product stream with the passage of time. And after some time, we will find that the 2,4-dichlorophenolic compound concentration in the product stream will be reached to 95% of the inlet stream concentration. At that time, we will find the breakthrough time, and we will regenerate after that time our adsorbent. We will regenerate our adsorbent after the breakthrough time. So now click on this one and drag this one. Here you can see that the time axis. So with the passage of time, the concentration of 2,4-dichlorophenolic compound in this product stream, this is nothing. This chart is nothing. This is the breakthrough curve, and it shows the concentration of 2,4-dichlorophenolic compound in the product stream with the passage of time. This is the time. So we can give time, like I'm using the time axis, like the from 0 to. I want my simulation to run from 0 second to, for example, 1300 second, and the time axis value is suppose 1300, and the grid interval, the distance between these 2 points, like these 2 points will be suppose 100. Okay, okay, here you can see okay, 200. Okay, the unit is suppose 1. Okay, now we will go to run option, and here this is initialization. So I want my simulation to go to the dynamic. I want to fast my simulation from 0 second to 1300 second. So here you can see 1300 second, pause it at 1300 second. Okay, I'm pausing it. This one, okay. So this is the breakthrough curve. This is the time axis and second, and this is the concentration of 2,4-dichlorophenolic compound in the product stream. And the unit here you can see kilomole per cubic meter. Okay. So now good. This is the dynamic, and click on run option. So this is the time. Here you can see 1200 second, 1300. Okay, it is completed. Now here you can see this is the time, but here this is the constant. Here you can see constant after 100. After this one you can see it is constant. So I can change my time axis from, suppose I want it to be at 300 second. Okay, this one, and the grid, suppose I want to this one to be 10, this one 10, 10. Okay, so here you can see 10, 20, 30, 40 second, 50 second, etc. So here you can see this is the breakthrough curve, the breakthrough curve. And here you can like go to the property. You can change the color, like this one. Click on this one, click on OK, or suppose go to the property, click on this one, change its color to this one, and click on OK. So here you can see I can change the color. Similarly, you can this one. Okay, you can go to the x-axis label, x-axis. Okay, grid. So liner and marker. Suppose line and marker. Click on OK. So here you can see this is line and marker. So you can play with these plots. Now here you can see the breakthrough time when the inlet. This is the inlet concentration, and this is the outlet concentration. The concentration of the 2,4-dichlorophenolic compound in the product stream So here, with the passage of time, in the beginning, the concentration of 2,4-dichlorophenolic compound in the product stream was zero, and after a certain time, it increase, and it reach to some specific constant value. And here you can see this is the point where this where we can obtain the breakthrough time. So the breakthrough time here you can see about 28 or 29 second. So this is a 20 to 30 second. So this is the breakthrough curve for this experiment. The breakthrough time is about 25 or 26. It is between 20 and 20, 30 second, the breakthrough time. So the outlet concentration reached to 95% of the inlet concentration at the breakthrough time. So from here you can obtain the outlet concentration after 130 second. Like for example, after 120 second, the concentration of the 2,4-dichlorophenolic compound in the product stream is this one after this. In the beginning it was zero, after 10 seconds it increased, after 20 seconds it further increased, like this one. So after this time, this here you can see after 40 seconds the adsorbent layer is saturated after 40 seconds. So after 40 seconds we will close our feed flow rate. We will close the feed wall, and we will regenerate the adsorbent, which is activated carbon, and we will restart the process again. Thank you very much for your attention. If you are new to the channel, please like and subscribe. Thank you very much.